Hello, everyone. I'm Mark Spencer. My background here, actually in Huntsville, was primarily in telecom before I got into airplane stuff. But I'm here to talk to you guys about what I call the softening of Ware. So kind of moving up from more hardware-oriented things to more software-oriented things. And I'll talk a little bit about telecom, aviation, and how I see this potentially impacting radio and how significant the role of SDR. All right, so I'll start out with just kind of a brief history of stuff. So this is really kind of the focus of the talk today, is that over time, the things that a user experiences about technology has shifted from the mechanical up towards more electrical-oriented things, up to firmware, up to software, and eventually up to configuration. This is a trend you're kind of seeing across all of technology. In some sectors, this has moved more rapidly than others have. So in short, mechanical things tend to get replaced by electronics. So if you think about cars, carburetors were a purely mechanical device to be able to mix your air and your fuel together, and those got replaced by electronic fuel injection. Electronic components are tending to be replaced with firmware. So audio mixers used to be sort of analog devices, and now they've kind of gotten to where they're more DSP, well, built around DSPs, embedded processors that will do that mixing for you. Firmware is tending to be replaced by software, and probably the most awful example I could think of was wind modems, for those of you guys that remember those days. And software is now being replaced by configuration, like if this, then that. Meaning that capabilities, end users, the wetware, right, the softest of all of it, is getting more and more able to interact with and manipulate what the experience is. So my first experience in open source was actually a project called Game, which was an instant messenger. I don't know, has anybody here ever used Game? Okay, so a few people. Back when I was in high school, I wanted to figure out how to write a graphical application for Linux, and an instant messenger seemed like a good application at the time, and that's kind of how I got started with Game. And then from that kind of gave me a taste for open source. And then later on, being this kind of Linux guy that I was, everybody was kind of asking me for help, tech support. I decided, why don't I try making a business out of that? So I had this tech support business, and I needed a phone system. They were definitely very expensive at the time. And at the time, as a college student, of course, the value of time was much less than the value of money, which led to the concept that using this leftover equipment I had from a co-op project, I could just figure out how to get a call into the PC. I made the features that I needed and gave away the software as open source. And sometime after that, probably by a couple years, realized that that open source telecommunications project Asterisk was way more interesting than the tech support business and way more fun for me to work on than the tech support business, and refocused around that. So architecturally, Asterisk essentially said, I've got all these different kinds of telephony interfaces, and they were kind of at that time there was this transition between analog and voice over IP. So you could take all these different kind of telephony services, bring them in to this kind of middle API, and then the developers, application developers, could then write applications that could run across all of these different interfaces, and regardless of whether you're dealing with an old round dial analog phone or a modern voice over IP phone, all this capability could be written once, and you could kind of plug into existing systems without having to completely replace an entire phone system. And at the time, that was a really dramatic breakthrough because people were not really sure if voice over IP was going to be a trend that was going to take off or not. So in the big scheme of things, this is all, of course, in retrospect, looking back. telecommunications started as a literal mechanical plugging of things. You know, here's one phone line being connected physically to another, to the idea of using switches and circuits to do that kind of more in an automated fashion. And then eventually to the idea of, oh, we could use microprocessors, embedded microprocessors to do this functionality, to the part where I came in, which was in the 2000s, taking Asterisk and making this whole thing become a software problem. And then finally, moving on to where the configuration was what the actual user interface for the customer was. So when you were interacting with it, you were mainly working on configuration. Oh, wow, there's an airplane. So, yeah, airplanes. The most important thing is that they are a lot more interesting than phones are. Now, this isn't to say that phones can't be fun. I have to tell you that it was extremely exciting the first time I could actually connect a phone to my computer and I made it ring and you'd pick it up and you could hear dial tone and I would show my friends and they would not nearly share the same excitement that I was. But I will say that with airplanes, it's much easier to find people who share that excitement. And amazingly, airplanes struggle today with the same problems that I was dealing with around phone systems in the early 2000s. So this is kind of a staggering statistic, but particularly on the military side, the cost of developing a new airplane is, the vast majority of it is actually the software, right? I think that's, to me, that is just a mind-numbingly hard number to get over. The idea that the software is what drives the cost of this development. But anyway, basically what happened is, you know, I had this telecom business. It started getting big, and I'm really kind of more of a small company guy. And as part of that, I decided I was going to learn how to fly. I wanted to do something different. And then discovered that, hey, here's all the software in airplanes, and it's, you know, it has all these weird challenges, unique safety critical requirements. You know, it was very obvious that flying could be a lot better if there was better software. It was still being sold as hardware, so if you think about, imagine yourself going to Best Buy and saying, hey, I'm setting up a new office. And they said, okay, we're going to sell you this computer to be a word processor, and we have this other computer we'll sell you that's a spreadsheet. And here's this third computer over here that can connect to the internet. And if you buy them all from the same company, you might be able to wire them together and get them to trade data between each other. You'd, of course, say, that's ridiculous. I just need a computer that can run these different applications. And yet somehow, in aviation, we have just accepted that that first model is the way things work. So it occurs to me that I've kind of had this story before, and wouldn't it be fun to do another startup? This is kind of like, I don't know if any of you guys have kids that have moved out of the house. So I don't have any kids, but I was one once, so I feel like I can speak about this. But it's sort of like if you were a parent and your kids moved out, and in your head you sort of thought, wow, wouldn't it be great to have a baby again? And you forget about like all the work that was involved in those early times. That's kind of what happened to me. And this time, a little bit different. I wanted to actually monetize the software through the software. Definitely different technical challenges and certification challenges. But the architecture actually is very similar to what goes on with Asterisk. So there are a few differences, but for the most part, you have physically how you reach out to all these different devices, whether they're screens or radios or sensors, bring them all in, and then these little microservices that are built on a common API to be able to hook them together. Details of that are not really the focus of the presentation. The important part was avionics, again, same sort of thing. We had physical instrumentation that was based on physical principles. So like an airspeed indicator in a traditional airspeed indicator is literally a form of a barometer that is comparing the static pressure, the just sort of ambient outside pressure, and the ram air pressure. Similarly, an altimeter is literally just a barometer. And so most of those instruments don't even need electrical power to be able to operate. And then from there, There was movement to electrically powered instruments. And then from there to the idea that you've got kind of firmware, they're specialized software designed to run on a very specific bit of hardware. And then what we're trying to do is to essentially build avionics as software to do just portable code and microservices that can implement what appears to be a very integrated experience, but is really all these individual pieces. And then eventually moving into where the configuration is what actually drives the majority of the features of the aircraft. So how does all this come back to radio? Well, obviously, we don't know of any aircraft that use wired data connections to get back to the ground. I think there maybe was a missile at one point that had a fiber optic cable, right? The TOW? That had a fiber optic cable that came out the back, but we don't really do that with airplanes. Yeah. So there are a bunch of applications, actually, of radio in airplanes. So there are communication-related things, VHF, UHF, what's called CPDLC, which is a data link for communicating between the pilot and the controller using kind of like text messages. There's addressing reporting, ACARS. You guys may have heard about this in the sort of lost airplane, the one that was lost over the Indian Ocean. And sat phones, there's data link products for being able to get weather imagery, text products so that you can know what the weather is like at your destination and to see what radar pictures look like for storms along your way. Engine trend monitoring, so the ability, particularly on turbine airplanes, to be able to monitor the condition of the engines and be able to detect trends if something is starting to go wrong. Of course, music, TV, internet, but you also have all your ground navigation. So VORs and ILSs that are still widely used today, as well as the obsolete things like non-directional beacons and marker beacons. There are satellite navigation, obviously GPS and related functionality, WAAS and LPV that can provide pretty incredible approaches that are very, very precise for getting you into airports in low visibility conditions and many times being able to land them. And then deconfliction, that is the detection of other aircraft and being able to avoid running into them if ATC drops the ball and doesn't keep you separated. So our big change that we've done in evolution is essentially to say, here's all these different computers and devices that in a typical aircraft are all separate. So they all have, maybe different processors. They all have different software running. But you have to have all these specific computers. And our idea is you can put all those on sort of common computers where you can just have multiples of them for redundancy. So you don't have to worry about losing, your autopilot computer or your FMS computer because you can just have redundancy in the actual computers and the rest of it is just software that doesn't weigh anything. Of course, the big change that I'm reaching out to you guys, the radio community, about is that these radios still, to this day, even under our system, are all separate radios. So your transponder, your comm radio, nav radio, even the things that are receive only are separate kind of distinct elements. And new capability typically is going to require the replacement of a new radio or the addition of a new radio to a system. And it gets hard to pull that functionality in and make it more widely available. Once you do start getting all this data in the same place, it becomes easier to start thinking about applications that you can't do with conventional equipment. So for example, on the evolution side, we can, because we have access to all the aircraft data in our architecture, we can verify data that has different discrete sources. So things like the angle of attack that you're flying with the airplane, which is how you detect approach to stall, has a physical relationship with the indicated airspeed, the weight, and the G-force on the aircraft. We have a place to be able to see all that and to be able to improve the quality of the data. Similarly, on radio, if you're doing SDR, you might have the ability, for example, to monitor an emergency frequency and have that available even while you're tuned to another frequency for your main communication. Those things essentially don't exist in hardware ones right now, but the opportunity is there to be able to do all that. Not to mention the idea that you could have navigation and communication could be on the same physical radio, and you could, in software, switch the functionality so that maybe you only have to have 3 radios that could provide you all your functions with an appropriate level of redundancy. So, in summary, tech gets softer over time. Iterative innovation gets faster and cheaper. So that is something that largely does not exist in aviation right now, iterative innovation. That's something we're trying to drive. Airplanes are really cool. Tech in aviation has lagged the rest of our lives. We certainly think that there are many opportunities to take relatively simple technology. I mean, when we describe how our stuff works, most of you probably think, why is that not how it's already done, right? There are many opportunities to take tech that has existed in lots of other sectors and make a big difference in how it works. So please help leverage the promise of SDR to improve the safety and to make aviation more economical. And also, we're looking for software developers if you guys know any or are interested. And I guess that's it. And I'm going to reserve the rest of the time for any questions that you guys might have.
Thank you very much, Mark. Okay, do we have any questions? Okay.
Hey, thanks. Very interesting presentation. One of the challenges must be the very, very heavy international regulation, you know, in terms of avionics and airframes and all that sort of stuff. And I mean, that would seem to be, you know, myself, I'm a pilot. That is it's the biggest burden, right? Getting, you know, you can develop stuff, but trying to get it implemented, you have this huge regulatory mountain that you have to work with.
All right, so that is a great question, and you're absolutely right in that the certification is the primary driver of the cost of these systems. And so in developing our software, our focus has been on 2 elements. One is you reduce the number of requirements and prioritize that, because essentially RAM, CPU, memory, all that stuff is virtually free compared to the cost of the certification. The second element is that we drive more of the capability into configuration, which means that we don't have to reopen that software certification as often to be able to make changes to the aircraft and to improve requirements. Now, even against that backdrop, on the civilian side through the FAA, around what are called Part 23 airplanes, so these are basically 19 passenger and smaller aircraft, the rules have changed now to be less prescriptive about how you have to show compliance with the rules, and now are performance-based, that you have to demonstrate that you can meet the specific performance requirement, but they're not describing how you have to be able to do it. And specifically on the software side, there's this thing called DO-178 that is kind of the big burden that you have to carry around software cert, which is essentially a very complicated and expensive way to show that your software implements the requirements that you set forth. There's an appetite for alternatives to that for how you can demonstrate software safety other than just through DO-178 on the FAA side. So in that sense, there are avenues for certification for new avionics that are much less onerous on the civilian side, at least. On the Army side, or on the military side, that's a completely different picture, and it's not clear to me yet if there's going to be an appetite for it. And so we have to kind of prepare for DO-178 anyway, but there are avenues that you can be able to get to that are being approved without the traditional certification process, using other methods of showing software safety.
Okay. Right here, and then I'll come back to you.
First off, thank you for the presentation. I think that mixing aviation and software is very interesting and important. One of the things that is a concerning factor about merging radios into one box is that with the current system with a whole bunch of different radio boxes, you can swap out one, do a software update to it, have that certified, and you're all good. If you merge them all into one box, how would you convince the FAA that the configuration change on the VHF radio wouldn't influence any of the other antennas, because these guys don't write radios for a living, right?
Okay, so this is a problem that to some degree we cross anyway, because we obviously run lots of applications on a common CPU. There is an airing standard called 653 for partitioning that essentially hard partitions processors where everybody gets a known time slot, a known amount of memory, and these processors are completely isolated from one another. So in that context, a software-defined radio could have multiple, essentially, time slots on the processor that's running it to be able to run different processes, and you might not necessarily run the same process at the same time. In other words, you might say, for example, I want to have 3 radios that can function either as COM or as NAV or as, let's say, ADSB weather receiver, and I may not necessarily need to have all 3 of those functions at the same time, or I might say in the event that one of them fails, I can get away with just 2 of them and give up that third element of functionality for the duration of a flight because it's not as safety critical. Those are the kinds of things you might be thinking about. They don't all necessarily have to be the same way. And I'll also say that I'm thinking about SDR probably more on the receive side than on the transmit side, because I know there are limitations on how flexible you can be on the transmission side.
Hey, thanks for the presentation. I have one question, well, 2 actually. One is related to safety. Like, how are you considering, or how are you making the mechanism, the software safe to like malicious attacks through, I mean, now if it's SDR, if it's all in one box or in one software, it could be prone to like hacking or something, right? And it's critical that safety is.
So that is also a really good question. There are lots of buses on a typical aircraft. So on a conventional aircraft, if you have physical access to the avionics buses, there is certainly no security to keep you from injecting improper data onto the bus. The architecture that we have chosen gives us the ability to reduce the attack vectors by using Ethernet as a common bus, and of course you can protect Ethernet with kind of standard security methods on Ethernet. That stuff's very well understood. And for the data that necessarily comes in from legacy devices using other buses, again, we've got this sort of place where you can compare data from different types of sensors that are connected to radically different systems in the aircraft where there should be physical relationships to be able to kick out bad data. And that is something that is very new. And it's really intended primarily to avoid the possibility of a sensor failure causing a more catastrophic accident. But it also can be used to help remove a compromised sensor or system of sensors from the mix of what the aircraft is considering.
Okay, just another question real quick. So you mentioned software redundancy for safety, but are you also considering hardware redundancy?
You said hardware?
Hardware, yes.
Yes.
What if the box fails? I don't know, the RAM is no longer functional.
Yeah, of course you can have multiple computers in this scenario. They could be dissimilar computers, and they could run dissimilar operating systems. So there are other ways, there are other elements that you can use, again, to help protect the system through redundancy. But a big piece of this is the idea that you should, if you reduce the overall types of computers that you have to have, then now you can sort of decouple the software and the hardware elements, and you can upgrade the computers as you need to upgrade the computers separately from the software experience, the pilot training experience, and so on.
Do you have any white papers describing your security protocols and your approach?
We have We have a little bit of limited information about how we are protecting the configuration through encryption and signatures. At the data transmission level, that is just Ethernet. So we're just right on top of IP UDP packets, right? So you would use the same techniques to protect the Ethernet that you would otherwise do. That right now is kind of outside the scope of what we're concerned with, because that is a very well established problem of how you protect IP UDP.
Yeah, factories have the same sort of problem with SCADA. SCADA is a control that was never designed for any kind of security. So now they're connecting them. So I see a parallel between what you're trying to do and what I've got to go do too.
Okay.
So anyway, thank you.
Sure.
Yep, Mark's up, Marcus.
So first of all, thanks for game, because your high school nerdery enabled my high school social life. That was cool. Also, a remark on that. It seems like you're doing something very similar to what the EE teams in car system manufacturers are doing, right? They're doing ECUs that kind of centralize a lot of functions, kind of merge a lot of different legacy buses, have Ethernet interfaces, have other kinds of interfaces. Ethernet might not be the choice for some kind of communications. But what I'm mostly concerned with is you're drawing a line between configuration and software, right? You say configuration is cool because it doesn't have to be recertified. It's just, you say it's something different, and I'm not quite sure where to draw that line.
Sure. It is not that you don't have to certify the changes to the configuration, but the methodology is different. The configuration is about the safety analysis and saying, I'm changing what the requirements are, and I want to demonstrate that this new set of requirements is safer than the old set of requirements, okay? But then the second piece is, if you have to change the software, you now have to reopen this whole question of demonstrating that your software implements the requirements that you spelled out. Whereas through configuration, we can change the requirements because we have already certified that the software meets the requirements of how to interpret the configuration, and now you can just produce the configuration. So another example is there are tools that exist in which you can lay out, essentially model a system, and the tool itself has gone through the certification to show that the output of the tool implements the requirements of what you put into the model. And so that generated code does not have to go through certification. It's considered passed already because the tool itself has been certified to be able to produce that code. So the configuration is kind of a variation on that model.
Okay. Thanks.
I have one. Related to Asterisk. Have you ever run, actually, show of hands in the audience for who has run OpenBTS with Asterisk attached to it? Did you ever run OpenBTS with Asterisk attached to it?
I did not run OpenBTS. Okay. I thought it was really cool, but
yeah.
I do not have the radio background that, especially then, did not have any radio background. Now I have, I went from this to this.
It never gets much more than that.
Yeah.
All right. Are there any other questions from the audience? Oh, what's up, Doug?
So I'm guessing you're planning to have your source open. Is that true?
It is source available. But what we want to do is to license the source code of what we have produced to an OEM that can include it, that can use it in their aircraft, so they would be able to update it. Okay. It is not open source in the sense that we would give away the source code on the internet just widely for anybody to use. But it is intended that what we are licensing is source code for vendors to be able to make changes so that you're not locked in to a specific avionics company in the same way that you are today.
Okay, so sort of really where I was going was that is Do you anticipate any change in attitude from the regulatory bodies from having more people looking at the source?
The visibility, actually, it's funny that you say that, because for you and me, we recognize that having more people looking at the source code improves the safety. And from the perspective of the FAA, they're much more concerned about demonstrating configuration management, that there can't be a change to the code that is not somehow reflected or tracked. They're more worried about the idea of, well, as an example, when we talk to them about using Linux for avionics that would go beyond a certain level of safety requirement, their biggest concern with Linux was being able to show that someone could not put a modified version of Linux on the device and not have that information be available to the pilot. So it actually tracks almost inversely from the way you would think that it would from the regulatory body. But again, under the new rules, it's sort of back in our court to be able to demonstrate the importance of that, the importance of the access to the code.
Any other questions for Mark? No? Just a couple minutes early.
All right.
Thank you so much, Mark.
No problem.